Hello everyone, I am Ekin Bircan and this is my EE515 term project design of an 8-bit digital to analog converter. We have given some design requirements, but for save some time, you can pause the video and read them. Actually, there are two slides. This is the second one. You can also pause from here. For our digital to analog converter, we are asked to design an op-amp to buffer the output. This is the schematic of the op-amp that I designed for this purpose. We have a current mirrors biasing circuit here, and we have three stages as you can see. And the first stage was a differential amplifier, and we used PMOSs for input so that the output of the op-amp can go down to 0 volts. You can see the open loop gain and phase of these designed op-amp. We have around 110 dB of gain in the low frequencies, and we have a phase margin of 50 degrees, which satisfies the design requirements. And we also asked to show the output and input characteristics are linear, so that you can see that when the input voltage is 0 volts, the output is 0 volts, and the curve is quite linear. Also, we are asked to use transmission gates. I choose to design my own transmission gate for the analog switches of the R2R network. And this is my transmission gate schematic. I use an NMOS and PMOS of equal sizes to high side and low side switching. You can see the R2R ladder network from the figure here. We have the flip-flops for input. We have the transmission gates, and we have R2R ladder network, and VH and VL is for the inputs. You can see the close-up view for the previous schematic here. I used the R value of 22K. And this is the test bench that I designed to show that the transient response of my DAC. You can see the transient analysis for all the inputs of the DAC. We have a quite linear response from all ones to all zeros. But we have a quite problem here, but I solved this issue from another iteration of my design. You can see the layout that I designed for my op-amp that I showed the schematic before. I used the meandering resistor to save up some space. And the biggest problem is that to fit this capacitor here. But overall design has an area of 0.38 millimeters square. You can see that after designing the layout, I did an analog extraction to see the open loop gain and phase of the op-amp again. My gain dropped to 80 dBs, but I still have a phase margin of 43 degrees, which is good. And also I checked the linearity of the output and input, and this is still conserved, and so that it still satisfies the design requirements. You can see the layout that I designed for our R2R network. We have transmission gates here, flip-flops here, and I used bus mechanism to save for digital inputs and the clock. And we also have two buses for VH and VL. And I also used again meandering resistors to save up some space. Overall design has the area of 0.5 millimeters square. You can see the layout that I designed for transmission gate. It has an area of 3200 micrometers square. And you can see the overall design of the DAC, which holds we have the resistor R2R ladder network here and the op-amp here. And the overall design took 1.5 millimeters square. And it satisfies the design requirements. Thank you for watching. This is my EE515 term project for this fall semester of 2021 and 2022.